In this lesson, we're going to start the new topic of trigonometry, or rather, continue trigonometry as we've already met this in the higher course previously. In the first lesson, we're going to look at compound angles. Now, we've already met things in maths before like compound area or compound volume, where we either add two areas or two volumes together or we subtract them to give the area or volume that we're looking for. And this is no different. Examples of compound angles might be the sum of 45 and 30, which gives us 75 degrees. And if we have 15 degrees, that's the difference of 45 and 30 degrees. So those are examples of compound angles. So, I've got a task for you here. Using your calculator, I want you to find sine of 45 plus 30 and the sine of 45 plus the sine of 30. If you pause the video and go and do that just now, and then come back until we discuss the answers. Okay, welcome back folks. Now for this first one, hopefully you've put that into your calculator and you've got an answer of 0.966 to 3 decimal places. And you can see here that we're actually finding the sine of 75 degrees. For the second one, sine of 45 plus sine of 30, when you put that into your calculator, hopefully you've managed to get 1.207 to 3 decimal places. And hopefully you've realised that sine of 45 plus 30 is not equal to sine 45 plus sine 30. And a lot of people might assume that these are equal because if we're expanding algebraic brackets, if we've got an algebraic or a numerical coefficient here, we can multiply this coefficient of the bracket by everything inside the bracket and we would get something that looked like this. But you need to remember here we're dealing with a trigonometric function, so these are not equal. And if we generalise that for any values of a and b, we can see that sine of a plus b is not equal to sine a plus sine b. So, what is sine of a plus b actually equal to then? Well, that is sine a times cos b plus cos a times sine b. Now if we look at the equivalent statement for subtraction, so sine of a minus b, we've got sine a cos b minus cos a sine b. So we've seen the two expansions here for the sine of compound angles. What about the cosine of compound angles? So firstly, cos of a plus b is equal to cos a cos b minus sine a sine b. And for cos of a minus b, we've got cos a cos b plus sine a sine b. So if we just have a wee look at some observations here. So we've got sine a plus b, and you'll notice that sine a cos b is, we are adding on cos a sine b. So just an observation to see that when we're expanding something with sine, we've got a positive inside the bracket, we've also got a positive when we expand. And the similar thing happens for sine of a minus b. However, when we look at cos, we can see that we've got cos of a plus b, and the expansion involves a subtraction. And for cos a minus b, you can see that the expansion involves an addition. So, to summarise all of that, we can put all of these statements together, and this, folks, is what you get in your formula sheet in the higher maths exam. So we've got sine of a plus b is equal to sine a cos b plus cos a sine b, and then if we look at the bottom, sine a minus b is equal to sine a cos b minus cos a sine b. And you can see for cos, we've got sine of a plus or minus b is equal to cos a cos b minus or plus sine a sine b. So you're given that in the exam, you don't need to remember that, but obviously sometimes it is faster to remember things so that you're not having to spend lots of time looking for things in the formula sheet in the exam. Either that or you familiarise yourself a lot with the formula sheet so that you know exactly where to find things. So let's look at some examples here. We want to expand and simplify cos of x plus 60. So that is equal to cos of x times cos of 60 minus sine of x times sine of 60. Okay, so you can see that we're getting this expansion here from here, and we're using the plus here and inside the bracket, so that means when we expand we're using the minus. So cos x times cos 60, well, we know that cos 60 is equal to a half, minus sine x, and we know that sine 60 is equal to root 3 over 2. And we can just write that more neatly, saying a half cos x minus root 3 over 2 sine x, and that's our final answer. So I would pause the video just now and take this down in your notes and then come back for examples 2 and 3. Okay, welcome back folks, and we'll look at example 2 this time. Okay, so we want to show that sine of a plus b is equal to sine a cos b plus cos a sine b for a equal to pi over 6 and b equal to pi over 3. So this is a proof question. We're asked to show that. So we want to take each side of this equation here and substitute in separately. So sine of a plus b firstly, and we know that a is equal to pi over 6 and b is equal to pi over 3. Pi over 6 plus pi over 3, in your head you're thinking that's 30 plus 60, that's 90 degrees. But we're working in radians, so that's sine of pi over 2, and we know that sine of pi over 2 is equal to 1. If we now take the right hand side of the equation, we've got sine a cos b plus cos a sine b, and we substitute in the appropriate angles for a and b. So we'll have sine of pi over 6 multiplied by cos of pi over 3 plus cos of pi over 6 multiplied by sine of pi over 3. And we can use all of our exact values here. Sine of pi over 6 is a half, cos of pi over 3 is a half, cos of pi over 6 is root 3 over 2, sine of pi over 3 is root 3 over 2. So carrying out the multiplication firstly, we get 1/4 plus 3/4, and then carrying out the addition, we get 1. We can see that both of the substitutions that we've calculated here are both equal to 1. So we can say since sine of pi over 6 plus pi over 3 is equal to 1, and sine of pi over 6 cos pi over 3 plus cos pi over 6 times sine pi over 3 is equal to 1, sine a plus b is equal to sine a cos b plus cos a sine b for a equal to pi over 6 and b equal to pi over 3. So we need to summarise the statement at the end. We need some sort of statement for the proof to actually show that we have proven what was asked for in the question. So just now would be a good time to pause the video and take down this example in your notes. Okay, and example 3 this time. We want to find the exact value of sine 75. So the solution then, I am going to express sine 75 in terms of angles which I know the exact values for, if I had to apply them to trigonometric functions. So I know exact values for 0, 30, 45, 60, 90, I suppose 180, 270, 360, etc. And for sine of 75, the best ones to use here are 45 and 30. Now sometimes people might think they could use 90 and they could subtract 15 from that, but unfortunately 15 degrees, if we apply that to a trigonometric function, we don't get exact values from that. We don't know those exact values. So 45 and 30, finding the sum of those would be the preferable option here. So we now need to expand that. So we get sine of 45 cos 30 plus cos 45 sine 30. We can then substitute in our exact values. So sine of 45 is 1 over root 2, multiplied by cos of 30, which is root 3 over 2. We're then adding on cos of 45, which is 1 over root 2, and multiplying by sine 30, which is a half. When we carry out the multiplication here, we get root 3 over 2 root 2, plus 1 over 2 root 2. Expressing this as a single fraction gives us root 3 plus 1 all over 2 root 2. Now this would be an acceptable answer at this point, but we might want to rationalise the denominator. So in order to do that, we need to multiply by root 2 over root 2. That's the equivalent of 1. And carrying out that multiplication gives us root 6 plus root 2 all over 4, because our root 2 times root 2 is 2, multiplied by 2 gives us 4. And that's our final answer there. So just now would be a good time to pause the video before the screen goes blank, copy down example 3 in your notes, and make sure that you complete the assigned exercise for today.